Okay, so welcome to Math 140 Calc 2. This is lecture 24. And what we're going to be doing today is we're going to be reviewing Taylor series very quickly. Then we're going to talk about fast ways to find Taylor series involving standard functions. So this goes back to a fundamental tenet of mathematics. Mathematicians are lazy. Once you learn how to do something, whatever you are given, you try to figure out, hey, can I somehow convert this to a problem I already know how to solve? And if so, then that's great. We'll talk a little bit about bounding the errors between Taylor series. So we know a Taylor series approximates a function, hopefully. We know it has to agree with the function at 0 because they're forced to agree at 0 is the expansion point. But how much is the error? And so we'll talk about how can you bound the error using mean value. I am not going to give the best bounds. I'm going to give the easiest bounds to get. With a little bit more work, you could gain a little bit more. You really get the correct dependence on the movement from the expansion. So we'll see what the correct, if we move 0.001 as a function of 0.001, what should the scale be? So we'll get that dependence correct. We won't get the correct constant. If we might be off by a factor of 100 or something like that. But that's not what really matters. What really matters is it linear? Is it quadratic? Is it cubic? And not surprisingly, the more terms you take, the better fit you should get. If there's time, I'll talk a little bit about multivariable Taylor series. What would you see in Math 150? Interestingly, most of the multivariable Taylor series we do, you can actually bypass all of the multivariable calculus if you remember the fast way to find Taylor series, which is one of the reasons I really want to emphasize that. And then I want to continue to talk about applications. And so one of the applications I want to do today is I want to talk about streaming video. And for those of you who are watching through Zoom today, if you have any questions, please just speak up. I will try to be watching the chat so that I will notice, but if not, just call me on my phone in case I'm missing something. I'm making the computer in the classroom a co-host as well, so I should always. All right, so let's quickly review what is a Taylor series. So the Taylor series of degree n of x would be the sum, little n goes from 0 to big N, the nth derivative at the point A over n factorial times x minus a to the n. And so what we're doing is we're doing, if big N equals 1, it's the best fit line. If big N equals 2, it's the best fit parabola, and so on and so on and so on. If you write this out slowly, it's just going to be, f of a plus f prime of a x minus a plus f double prime of a over 2 factorial x minus a squared plus dot dot dot. This is where we start. This is the initial speed. This is the elapsed time. So this part over here is basically just the tangent line. So we've seen this before. And what we're doing by adding the additional terms is rather than just using my instantaneous speed and assuming that the speed is constant throughout all eternity, we're saying, well, let's take into account the fact that we know the speed is changing. So the next thing we can do is we can look at the acceleration, and then so on and so on and so on. And the big result is if I look at the nth derivative at a, this is equal to the nth derivative of f at a, if 0 plus equal to n plus equal to n. So the first big N derivatives of my function agree with the first big N derivatives of the Taylor series. What if I were to take n plus 1, big N plus 1 derivatives of the Taylor series? What would I get if I take n plus 1 derivatives? So what degree polynomial is Tn of f? Is degree 1. So if I take n plus 1 derivatives, what's n plus 1 derivatives of a degree n polynomial? It's just, well, let's say I give you a problem, ax squared plus bx plus c, and take 5 derivatives. What would you get if you took 5 derivatives of the problem? You get 0. So if I take n plus 1 derivatives, I get 0. If I take n plus 2 derivatives, I get 0. So it's going to agree with the initial function for the first big n derivatives. And then from that point onward, all of its derivatives at A are going to be 0. Because once we've taken your n plus 1 derivatives, we have the 0 polynomial. Okay. So we don't expect it's going to keep agreeing, but it's staggered so that it will agree up to a certain point. And now we actually have a way to calculate Taylor series. All we have to do is take derivatives of our function and plug them in. So if our function is easy to differentiate, this isn't that bad. And so we've done this examples, if I give you f of x is e to the x, f prime of x is e to the x. So f of a would just be e to the a, f prime of a would be e to the a. And so what's the most common point that we'd use for a? Standard point we like to expand things about. 0. And so if we take a equals 0, that gives you f of 0 is 1, f prime of 0 is 1, f double prime of 0 equals 1. And it leads to the Taylor series e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so on. So whatever function I give you, we just have to start doing derivatives and put things together. And now we see why we spend so much time talking about when does a series converge. Because we want to figure out, well, does this function converge? And if so, does it converge to the function we care about? And remember, I will put it in red because this is a warning of how bad things can be. If I give you the function g of x is e to the negative 1 over x squared if x is not 0, and 0 if x equals 0, using L'Hopital, you can get that all the derivatives of g at 0 is 0. So any Taylor series of g is just the 0 function. Converges, but doesn't converge to g. And this should make you a little sad. I think we'll also show emotion from Americans. If you converge, all right, we should be done. No, it's actually possible for the series to converge not to your original function. What this means is Taylor series do not uniquely determine a function. If I give you 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, how much class time do I have? What function do you think this is converging to? So what function does this is? Cosine of what? So I was actually thinking cosine of x times 1701 g of x, g from the last page. And my daughter would draw a much nicer smiley face than this, with a nice yellow spoon. You can't tell the difference between the Taylor series of cosine of x and cosine of x plus 1701 g of x. Because if I take all the derivatives of 1701 g of x and 0 are 0. So there's a beautiful series of papers in physics in relation to, can you hear the shape of a drum? You can hear the different resonant frequencies. Is that enough to determine the structure of the drum? And this is a really big problem in science. When is a sequence of data enough to uniquely specify what you have? It turns out the Taylor coefficients are not enough to uniquely specify what you have. They are if your function satisfies a technical condition known as AX. And depending on how much math you take, you can get better statements of exactly what does it mean for the function to be X. What do you need for the Taylor series to uniquely determine the function? So you have to restrict the class of functions you look at. And what is the most natural condition? We're not going to get into this, but I want you to at least be aware of such issues. So now if I give you a function, it's now just a matter of doing some derivatives to find the Taylor series, and then using our tests to determine whether or not the series converges, and if so, for what region. Okay, so now let's talk about error analysis. So what I want to do is let's let E of x be the absolute value of f of x minus the nth Taylor series at x. And so I'll put maybe an E sub n to let myself know that this comes from taking n derivatives. I'm going to do things about x equals 0 because it's going to make my life easier. Okay? And so I want to study this. So let's look at f of x minus, tnf of x. This is going to be f of x minus f of 0 minus f prime of 0 x minus f double prime of 0 over 2 factorial x squared minus all the way down to the nth derivative at 0 over n factorial x to the n. All right. So let's look at f of x minus f of 0. We've actually seen that theorem in this past. You've also seen it, I believe, in Calc 1, that allows you to approximate f of x minus f of 0, or even to evaluate it exactly if you don't need it. So how can I write f of x minus f of 0? Anybody know a good theorem to use? Mean value. So by the mean value theorem, excellent. Make sure you send me an email. What would that difference equal? So normally we would divide this by x minus 0. So normally we would say f of b minus f of a. So mean value theorem. F of b minus f of a over b minus a equals f prime of c. A less equal to c less equal to b. So because we have f of x minus f of 0, we're multiplying both sides by b minus a. So this is going to just be f prime at some point. I'm going to call it c 0 x times x. And again, I'm trying to have good notation. The x is to remind myself that it's depending on the point x, and the 0 is that it's depending on the point 0. So C0 lives somewhere between 0 and x. So C0x is between 0 and x. Minus f prime of 0x minus f double prime of 0 over 2 factorial x squared minus the nth derivative at 0 over n factorial x to the n. Okay. What do the instructions on a bottle of shampoo say? Lather, Mr. Keaton. How can you forget lather? I mean, I will not comment about how you. Right. If you just rinse and repeat, I mean, this is just exactly. There is. So, what do you think we should use to study f prime of C0x times x minus f prime of 0 times x? What should we use? Just talked about shampoo mathematics. Yeah, let's use the mean value theorem again. And I'll call, C1x is going to be between C0x and x. So this should be f double prime of C1x times C0x minus 0 times x. Right? Both terms have an x in it. Double prime of 0 over 2 factorial x squared minus 2 minus. How is this looking? Can we use the mean value theorem again easily the next time? No, things are now going to get hard because this is being evaluated at the point C1x, this over here is a C0x, and over here, this is a 0. So I could do this for a little bit. So this approach is actually not too bad if we're just doing, maybe a first order Taylor series expansion. And if I stopped in, if I didn't have the second derivative and all that stuff, this would actually be a very good approach. But unfortunately, this is starting to get really bad and really complicated in terms of trying to estimate the error. It worked out very nicely in the beginning. But now as I start to have more terms, it's going to be harder. So any questions about this? It's good to see approaches that don't always work. This was a natural thing to try. The mean value theorem shows me how close they are. Unfortunately, it doesn't do it. Let's do it another way. But I like the idea of using the mean value theorem. So let's try again. Take 2. So we have f of x minus tn f of x. Well, why don't I just directly use the mean value theorem? This would just be the absolute value of, let's define the function g of x to be f of x minus tn f of x. What's g of 0? That's f of 0 minus tn f of 0. What does that equal? So what's g of 0? What's f of 0 minus the Taylor series at 0? Well, the Taylor series at 0 is just f of 0. It's just 0. So notice, this over here is just our g of x. So this is just the same as g of x minus g of 0. Most great math proofs involve multiplying by 1 at some point or adding 0. We just added 0. Right? So we're letting g be the function we're trying to study. G is really our error function. Would people rather me use E for error rather than G? That's what we're used to. So by the mean value theorem, this is just going to be G prime at some point C, I'll call it 0x times x minus 0, which is just G prime of C0x times x. Everybody agree so far? Now, g of x is f of x minus tn f of x. So g prime of x is f prime of x minus tn f prime of x. What's g prime of 0? it's just going to be f prime of 0 minus the derivative of the Taylor series, that's 0. It's 0. We've chosen the Taylor series, remember, so that the first big N derivatives match. Right? So this is going to just be 0. So what I can do now is I can say our error is the absolute value of g prime c0x times x is g prime c0x minus g prime of 0 times x. And now how can I study g prime c0x minus g prime of 0? I've just added 0. How would I study that? What would I use? Mean value. And because we're taking derivatives, the problem we had before was I still had that 2 factorial before in the denominator. I had x versus c naught 0 times x. By using it this way, everything's going to work out. And so now I use the mean value theorem, and this is going to be g double prime. I'll call the point c1x, the next level, times c0x minus 0 times x. And so this is going to be less than equal to g double prime c1 of x times x squared, as c0x is less than equal to x. Absolute value. Right? Because we move somewhere between 0 and x. Well, what do you think g double prime of 0 is? We just added 0. Right? We can just keep adding 0. And so when we go into the next page, we have our error is less equal to g double prime c1x minus g double prime of 0 times x squared. This is going to be g double prime of, let's call it c2 of x times c1x minus 0, absolute value x squared. This is going to be less than equal to g double prime c2 of x times x cubed, as c1 of x is at most x in absolute value. But this is just g it should be g triple prime. Sorry, at this point it's not g triple prime. It's just g triple prime of c2 of x minus g triple prime of 0 times x cubed. And now everything is matching up very nicely. And now we continue the shampoo mathematics, and eventually this is going to be less than the n plus first derivative at some point c nx times x to the n plus 1. So f of x minus the Taylor series is less than equal to the maximum over, say, t plus equal to the absolute value of x of the n plus first derivative at t times x to the n plus 1. So this gives us a really nice control over the size of the error. If x is of size 1/10 and n equals 9, then the error is some constant times 1 over 10 to the 10. Now, if the constant is the amount of money that Elon Musk has just paid for Twitter, is offering to pay for Twitter, then that is enough to overwhelm the error. But if I keep making x smaller and smaller and smaller, this constant is fixed. Well, what do I mean by fixed? Fixed or decreasing. As t goes less than equal to x, if I make x smaller, I have a smaller range to look for the maximum value. So the maximum value can't get larger. It could get smaller as I restrict my window. So if I take x equals 1 or 1/2 or 1/3, whatever, then the maximum value I get for that, I'm never going to have to use a larger value than that as I go further. But I'm going to start getting more and more savings by the x to the n plus 1. So this tells us that the Taylor series are going to converge very nicely. And if you have a Taylor series of degree n, the error is going to be proportional to x, how much you're moving, to the n plus first power. And so if you move a very small amount, the error is going to be extremely tiny. Now, if the function is not n plus 1 times differentiable, you can't, of course, use this. So we need to assume the function is differentiable once more than how far we're expanding. And it's not a huge deal. If you have a function that's infinitely differentiable, not a problem at all. The more differentiable the function is, the more derivatives we can use, and it looks like the better deal we can do. Again, the derivative, the n plus first derivative, could get very, very large. But if we take a small and smaller window, that's going to be enough to overwhelm that. And so that eventually, if you're in a small enough window, there's going to be a huge gain. This is not the best job you can do. With a better analysis, I think you can get like an n factorial or something like that down to the denominator. If n equals 10, n factorial is respectable. To me, this is a good enough argument. It's really straightforward. I can just keep part of it repeating the value theorem. It really highlights what's going on. And I like how we try the most natural thing. Let's just look at the difference directly. Initially, it looks like, oh, we can just use the mean value theorem. We can use the mean value theorem. But after 2 attempts, we now see things are no longer properly aligned. And so it was a good idea. And this shows you sometimes that something that works for a while may stop working. So if I want to just do a 0th order or first order Taylor series, it does a great job. But as soon as I want to get to a second order Taylor series expansion, it starts to have problems. As an exercise, you could try to figure out, is there a way to fix this? But this is getting really bad. It's much cleaner to use something like this, where we're using the mean value theorem, and we're cleverly choosing things. Well, what does it mean for the Taylor series to have its first n derivatives agree? It means g of 0, my difference is 0. It means g prime of 0 is 0. It means g double prime of 0 is 0. Let's take advantage of that, and let's use the mean value theorem. So we just keep adding 0. Okay, so this is the theory of how well Taylor series do. So if I give you, cosine of x plus 3x squared, if this is my function f of x, what's f of 0? Cosine of 0 is 1. What's f prime of x? Root of cosine is negative sine of x plus 3x squared, but then I need the derivative of x plus 3x squared. So I get negative sine of x plus 3x squared, and I take the derivative, I'm going to get 1 plus 6x. So what's f prime of 0? Nope. What's the sine of 0? 0. For the second derivative, we could do this, but it's not going to be a product rule. And as we keep taking more and more derivatives, it's going to become more and more involved. And we have no desire to do this. Right? Now we know, here's the fast way. The cosine of u is 1 minus u squared over 2 factorial plus u to the 4th over 4 factorial minus u to the 6th over 6 factorial. What should we take u to be? X plus 3x squared. So now we get the cosine of x plus 3x squared is 1 minus x plus 3x squared over 2 factorial plus x plus 3x squared to the fourth over 4 factorial, and so on and so on. What can you tell me about x plus 3x squared squared? Will I have any constant terms? Will I have any linear terms? So this is only going to have degree 2, 3, and 4. When I look at x plus 3x squared to the 4th, what are the possible degrees going to be? 4, 5, 6, 7, 8. The next term, x plus 3x squared to the 6th over 6 factorial. What's that going to be? So if I want the degree for a Taylor series, it's going to just be 1 minus x plus 3x squared over 2 factorial. And now for the x plus 3x squared to the 4th over 4 factorial, what's the only term for that that's going to survive at degree 4? X to the 4th. So I'm only going to have the x to the 4th over 4 factorial. If you're able to just like get rid of it. Yes, because they're higher order. And this is the much faster way of calculating Taylor series. If I wanted the degree 5, then what I would have to do is I would also have to include the degree 5 term. And so then that would be a 4 choose 1 using the binomial theorem. And I would have x cubed times 3x squared. And that would be my degree 5 term. And I don't have to worry about anything from the x plus 3x squared to the 6. Because that's going to be a degree 6 term. So if I only care about finding up to the degree 5 Taylor series, I can stop. Basically just saying throw away everything else. So this is a really fast way to calculate Taylor series once you know a few basic ones. So if you know the Taylor series expansion for cosine, then if I just shove anything into cosine, just expand cosine out. Any questions about this? And I want to make sure we do at least one application of stuff. So steganography is the art of hiding digit in the image, for instance. So I'm giving some of this away. I'm assuming everybody has enough ability to recognize that there is a trade in this image. For $100, can anybody see the cat? The cat is at least 1/8 the size of the area of the whole picture. It is a big cat that is hiding in the tree. This is not a little dinky cat when I'm trying to sneak it by you. The cat is at least 1/8. So I'm going to show you how you can hide an image in an image. And this is one of my favorite applications of, if not Taylor series, then generalizations of Taylor series. So the whole idea of a Taylor series is to take a complicated function, and rather than sending the entire function, you can just send the first couple of Taylor coefficients, and the computer can reconstruct. So I am no longer going to ask, because everybody here watches something on streaming video. I'm going to just assume at this point in society, everybody has watched something on streaming video. If for no other reason than part of your homework is to watch the videos before class. So I know you're watching streaming video. So one way to transmit a function is you can transmit its value at a huge number of points. The more points you transmit, the better understanding you have of the function shape. Well, great, but the more points you transmit, the more expensive it is. And so what you want to do is you want to transmit as little information as possible. I am old enough that I remember dialing up through modems, and I remember how painful it would be to download files in the megabytes. We did not have streaming video. Or maybe we did, but it was like ASCII style. Was maybe I'll show that if there's some time at the end of class today. And so you had to be really concerned about how much information you were transmitting. Well, if I want to transmit a curve, rather than transmitting the curve, what if I just transmit a couple of Taylor coefficients? We just showed that the Taylor series is often a really good approximation to the function. If I transmit a few Taylor coefficients and the computer reconstructs the function, the error might be so small I might not notice the difference. And this is the idea behind a lot of information theory, is we don't have to transmit everything perfectly, we just have to transmit it well enough so that it is within the realm of what you can sense. So let's imagine we want to transmit a static image L by W. So we have W pixels. Each pixel is a triple. A lot of systems use the red, green, blue. We often do things in binary. Why do we do things in binary? So are you going to be the one who's reconstructing the image? Who's reconstructing the image? The computer. The computer loves binary. On, off, yes, no, off, on, true, false. So the computers love to work base 2. So we'll do things in base 2. So we often assign numbers instead of doing things in base 10, we'll do things in base 2. And so if we take n equals 8, so we're writing numbers from 0 to 255. So is anybody comfortable with writing numbers in base 8, so base 2 rather than base 10? So in base 10, 314 would be 3 times 100 plus 1 times 10 plus 4 times 10 to the 0. If I want to write this in base 2, 256 is a power 2 that's less than 314. 512 is more. So it would be 1 times 256. So to get from 256 to 314, I have to add 44, 54, 58. So it would be plus 0 times 128, plus 0 times 64, plus 1 times 32. I said I had to add 58. So now I have another 16, I think, that I have to add. No, 26 that I have to add, right? So I have to add 116. And I have to add 10. So I add 1 8. I add no 4s. I add 1 2. I add no nuns. And so in base 2, the number would be 1 0 0 1 1 1 0 1 0. We put a subscript 2 and tell us it's base 2. So really, there's no real difference between writing numbers in base 10 and writing numbers in base 2. And so if I use n equals 8, I have 256 choices for red, green, and blue. So if you look at all the possibilities, that gives me almost 17 billion colors. How many colors can you name approximately? 20. 20. I mean, it depends. Are you going to allow yourself jungle green, sunset orange, depending on how much we're good. We're not going to be anywhere near 17 million. If you look at your box of Crayola, if it's a really good box, we have 120 colors. We're talking here 16 million. And so the idea is the following. So take one of the colors red, and its numbers going from 0 to 255. So we can write it in binary. So R7, 2 to the 7 plus R6 to the 6 and so on. If we change just the last of the last 2 digits, it's a very small change. So each of these coefficients, what are the possible values for R0, R1, R2? We're writing things in binary. Each Ri lives where? What are the possible values for expanding something in binary? 0 and 1. So if I change just the last digit, I've changed the value of my color by at most 1. So 1 out of 255, that's about 0.5%. If I change the last 2 colors, that's a movement of at most 4. And so what I can do is the following. Let's take a white piece of paper and let's have some black text here. Let's write a secret message. Every place where there's a black pixel, we'll put a 1. Every place there's a white pixel, we'll put a 0. We take our image and now we change the last digit of red so that if it's a black pixel, it's a 1. If it's a white pixel, it's 0. The actual image we have is going to be slightly changed now, but the amount of change is going to be very negligible. And you can now hide an image inside an image. If I change the last 2 digits, I now have 4 possibilities. And on average, maybe I'm off by about 2 from what was true. Well, if I have 4 possibilities for red, 4 possibilities for green, 4 possibilities for blue, how many possibilities is that? Sure. So let's say I just changed the last 2 digits of red, green, and blue. So I have 4 possible colors for red, 4 possible colors for blue, 4 possible colors for green. So how many total colors do I have? How many triples do I have? I have 4 choices for red, 4 for green, 4 for blue. 64. So that means, well, okay, so I don't get the 128 Crayola box, but I get the 64 Crayola box. That's not bad. I can give myself 64 colors just by changing the last 2 digits. And so one of the ways you would often transmit video and whatnot is you might take like a snapshot and you might have, here's my red function for the entire space. And if your function is continuous, then you could just transmit like a FOIA, I'm sorry, like a Taylor series or a generalization of a Taylor series that doesn't look better. And so rather than transmitting the entire red function on the plane, I transmit like a 2-dimensional series of coefficients. If I transmit enough, I get a good sense. So up here is the tree. Last chance, does anybody see the cat? Cat is everywhere. The entire image of the cat is hidden pixel by pixel. And if you just look at the last, like the last 2 pixels, it gives me 64 colors to play with. And so you can hide an image very easily in another image. So some of the work I do is to try to detect, can you determine if somebody has modified an image? And there are tests that you can do. And so there's a lot of fascinating questions you can ask about stuff like this. So I want you to get a sense of what can you do with the math that you're learning in this class, what are the applications? This is an extremely powerful application. One of the things that's extremely important in war on terror or stuff like this is, can you detect chatter between different groups? Can you detect that there's a plan going on? If you can just post a message, they can just go online and look at this. You don't have to necessarily have communication back and forth. So can you tell if an image has been modified? There are 2 questions I've heard journalists ask, and it's a debate as to which was the stupidest question of all time that I've ever heard. One of the 2 was, within a day after 9/11, one of the big 3 networks was interviewing an airline pilot. And the journalist asked, so do you have any ways of communicating with people on the ground, ways that the terrorists don't know about, to let them know that something is going on? And you're absolutely shocked that somebody would ask you. And the pilot did a great job. He said, no, there's technical reasons why we can't do that. What's your next question? How can you tell if an image has been modified? Well, one thing you could do is you could actually just call off the last digit or the last 2 digits and see if something is being done. Well, if I know that there's a danger you're going to do that, I will have a more complicated way of changing the last 2 digits. I'll have a special little program as to maybe for the first digit, if I change, in fact, I don't want to say anything. I don't want to say anything because this is being recorded. There's no way to do it. It's always easy to detect, not even with investigating. So this is one of the really good applications of things such as Taylor series and their generalizations. Rather than transmitting tremendous amounts of information, you can transmit small amounts of information and use the fact that you have powerful computers on the other end to reconstruct. If you've ever listened to music, you don't have to have a perfect copy of the music because of the human ear. It just has to be good enough for us to hear. Right, so the last thing I want to do, because we've got like a minute or 2 left, is I wanted to talk about multivariable Taylor series. What if I give you the cosine of x plus, say, xy? and I want to expand this. This is a function of two variables. So you have to think, oh my God, what would a function of two variables be for Taylor series? Well, I know cosine of u is 1 minus u squared over 2 factorial plus u to the fourth over 4 factorial plus dot dot dot. So cosine of x plus xy is 1 minus x plus xy squared over 2 factorial plus x plus xy to the fourth 4 factorial minus x plus xy to the sixth over 6 factorial plus dot dot dot. If I want, the degree 5 Taylor series, it is 1 minus x plus xy squared over 2 factorial. And which terms do I need from the x plus xy to if I want to be degree 5? I could have the x to the 4th. And so that's 4 choose 0, x to the 4th. Or I could choose x 3 times and x squared once. 5 Taylor series in 2 variables. And I'm doing this without figuring out how do I write things down in terms of derivatives and all that stuff. Just doing it at a really high level. So this is an extremely useful trick. Once you know a few of the standard Taylor series, you're in great shape. So we've got a few moments, so I'll just write, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. We've done cosine of x so many times, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. Sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5. The natural log of 1 minus x is, I believe, negative x plus x over 2 plus x squared over 2, x cubed over 3 plus dot dot. And the natural log of 1 plus x is x minus x squared over 2 plus x cubed over 3 minus x to the 4th. So these are the really important, useful ones to notice. For the natural log of 1 minus x, if x is greater than 0, the natural log of 1 minus x is less than the natural log of 1, so it would have to be negative. Good, this is negative. If the absolute value of x is greater than 0, the log of 1 plus x is greater than the log of 1, so it's greater than 0. This is positive. So these are at least good, simple consistency. All right, so this is a good place to stop. So have a